All right, let's continue our discussion of reactions in aqueous solution. And so last time you said that if you have an ionic compound and it dissolves in water, it's going to give you ions in solution. And most molecular compounds, we said, will not give you ions in solution. The exceptions being acids and some weak bases. Okay, and let's take a look at examples of reaction that would result when you mix solutions that have ions in them. Okay, so one common type of reaction that you will encounter if you're dealing with solutions that have ions, okay, it's possible that you can get ions from the two different solutions that are able to combine to form something insoluble. So if you put together two solutions that are capable of that contain ions that can form something insoluble, then you get a precipitation reaction. So for example, let's say we were to mix lead nitrate solution and potassium iodide. Now if you have a lead nitrate solution, you're going to get lead ions there and nitrate ions evenly dispersed throughout your solution. Okay, so you have gazillions of these. And potassium iodide, you also have potassium and iodide ions all in your solution. Well, what happens if you mix these two together? Okay, so you can see that there's two new compounds that you could form that could possibly be insoluble in water. You can think of this as an exchanging of partners. So the positive ion from this one can combine with the negative ion of that one. Okay, so and the other possibility is a positive ion from potassium iodide. In this case, the potassium ion can combine with the nitrate. If any of those two combinations happens to be a compound that is insoluble in water, then you'll end up with a precipitate. And you can see right here, if you go back to your solubility rules, you will find that lead iodide is in fact an insoluble compound in water. So if you were to mix lead nitrate plus potassium iodide in aqueous solution, okay, then this combination of lead and iodide will give you something that's insoluble in water. So the product you get here is PbI2. Lead is +2. Iodide is -1. So when you put those two together, you get PbI2. That's your solid precipitate. So you put an S there. And what remains in solution will be your potassium nitrate. Potassium ions and nitrate ions in solution. So what happens when there's a precipitation reaction? Let's take a look at a video illustrating this. Let me see. If you go to the Moodle website, I have under reactions in aqueous solution, internet resources. Okay, let me see. Okay, so here's an example of a precipitation reaction between lead nitrate and potassium iodide. This is a video on YouTube. So what happens here is you have two colorless solutions. There's lead nitrate right there, and this one is potassium iodide. You mix the two, and right away you get that yellow solid that forms. Okay, so that's a sign that you have an insoluble compound being formed when you mix the two solutions, and that happens to be lead iodide. And you should be able to predict that that is lead iodide based on what we know about the solubility rules. So if you know your solubility rules, you can predict whether or not precipitation is going to occur. So that yellow solid right there, eventually that's going to settle down to the bottom of your test tube. So towards the end of that video, you have all of that yellow precipitate. Eventually, all of that's going to settle to the bottom of your test tube. Okay? So that's a precipitation reaction. All right, so that's a precipitation reaction. Now let's balance that equation. Let's practice balancing our equation. So what do we need to do? Lead nitrate plus potassium iodide gives you PbI2 plus KNO3. We'll just do this by trial and error. So I've got one lead on each side. That's balanced. Iodide, I have 2 on the right, so I need 2 Ki. Alright, and what else do I need? 2 potassium, so I'm going to need 2 potassiums right there. So that's my balance equation. Now, as you can also put a downward pointing arrow next to PbI2 there if you want to indicate that you're dealing with a precipitation reaction, that PbI2 is a precipitate. Now, like we mentioned last time, this is what we would call a molecular equation, where you're writing the complete formulas of the substances involved in the reaction. But this is not really the best way of representing what happens, because the only thing that really happened here, okay, is that your lead ions combined with, your lead ions right here combined with your iodide ions. The potassium and nitrate, nothing really happened to them. They were just there to begin with, and in the end they're still there floating around in the water. So the only thing that really happened was for potassium ions and lead ions and iodide ions to combine. So it's better to actually represent this. So this is what we would call a molecular equation. A more accurate description of what happened is you can say lead ions plus 2 nitrate ions. Okay, they're actually separated in solution, right? And potassium and iodide are actually also separated in solutions. So you have 2 potassium ions and 2 iodide ions yields. Now PbI2, the lead and the iodide ions after the reaction are together in the precipitate. So you write that as PbI2 solid plus potassium nitrate ions. The potassium nitrate, actually you don't form pairs of those. What you just have are potassium ions and nitrate ions left floating around in your solution. So this is what you would call, okay, there's 2 potassiums and 2 nitrates. This equation right here is a better representation of what happened. This is what you would call your ionic equation. Okay? If you're dealing with reactions where you actually have ions in aqueous solution, you write those ions separately because they're not going to pair up in solution. Most of them, a vast majority of them, will be separately, individually surrounded by water molecules. They're not together. So the lead and the nitrate, they're not together in water. They're separated. The potassium and the iodide, they're not together in water. They're separated to begin with. In the end, the potassium and the nitrates, they're not together in water. They're separated, each one of them surrounded by water molecules. So this is what you would call your ionic equation. Now, if you take a close look at this, you'll notice that, okay, any nitrate you have at the beginning will still be there at the end. So nothing really happened to the nitrate, like I said. So you could say that your nitrate are just spectator ions. Same thing with your potassium ions. The number of potassium ions you have in solution before and after the reaction remains the same. So that can cancel out. So you say your potassium and your nitrate ions are what you would call spectator ions. They just watch lead and iodide combine to give you PbI2. Okay? So you could say that lead and iodide got married. Potassium and nitrate are just the groomsmen and bridesmaids. They're not really involved in the reaction. Okay? So if you look at this, we can simplify our ionic equation by removing all the spectator ions. You're left with what is called a net ionic equation. So if I take out my spectator ions, I'm going to have lead ions plus 2 iodide ions gives me PbI2. This is actually the best way to represent what actually happened in this solution, in this reaction, okay? Well, the only thing that happened is your lead ions combined with iodide ions to give you a precipitate of PbI2. So this is the best way of representing what happens, and this is called your net ionic equation, okay? So what we call the molecular equation is the complete equation that has all the formulas of the compounds involved, substances involved in the reaction. Even though they're separated as ions in water, you write them as if they were made up of molecules. That's why it's called a molecular equation. A better term for that would actually be the complete formula equation. All right, but it's been traditionally referred to as a molecular equation. You're writing it as though everything was made up of molecules. And then when you actually separate the ions, okay, when you're writing the equation, then what you call for substances that are actually dissolved in water, ionic substances, then you have what's called an ionic equation. If you get rid of the spectator ions from your ionic equation, what you have left is called the net ionic equation, right? So here you have to go back and recall your solubility rules. Okay, do you expect precipitation from any of these mixtures, or neither, or both? Then you're going to have to go back to your solubility rules. And so let's take a look at choice A right here. You have sodium. It's made up of sodium ions and carbonate ions. The second one is made up of potassium ions and nitrate ions. Okay, so you have these in separate solutions, and then you put them all together. Is it possible to get a precipitate? And for the second one, you have silver ions and nitrate ions in solution, calcium ions and chloride ions also in solution. If you mix all of these ions together, can you form something that is insoluble in water? Do you need a refresher on your solubility rules? Okay, let's see. Go back to our solubility rules. Rule number 1. Okay, anything that has sodium, potassium, ammonium, nitrate, nitrite, perchlorate, and acetate. All of those compounds that have any of those ions would generally be soluble. So right there, from rule number 1, you can eliminate some of these choices in this question. If it has sodium or potassium, okay, then that compound is going to be soluble in water. So that means it's not possible for you to make a precipitate that has sodium. You cannot make a precipitate that has potassium. And going back to rule number 1, you can also say that there is no precipitate that has nitrate in it. So from choice A right here, then you don't expect any precipitation reaction. Okay. What about choice B? Okay. Right here, you can eliminate nitrate. Rule number 1 says all nitrates are soluble in water. Okay. So if a compound has nitrate is soluble in water, there's no way you can get a precipitate that has nitrate in it, according to the rules. So the other possibility is, well, calcium chloride, you already know it's soluble. It's in water to begin with. So the other possibility you have to look at is, will silver and chloride together form something that's insoluble in water? Well, you go back to your solubility rules. What did we have? Rule number 2 says, if you have a chloride, all chlorides, with the exception of those in combination with lead, silver, and mercury 1 and copper, okay, they are generally soluble. Okay, so we're dealing with a chloride here, so let's go back to our question, we have a chloride. So we say chlorides are generally soluble except in combination with lead, silver, and mercury, and copper 1. Well, this is silver, so that means AgCl is insoluble. So it is possible to get a precipitate from this mixture right here. So if I were to mix a solution of silver nitrate and calcium chloride, I would expect to see a precipitate. And what would that precipitate be? It's going to be silver chloride. And in fact, you can easily write the net ionic equation without really having to go through the full molecular equation. You can just say what's going to happen here is that the silver ions and the chlorine ions will give me something insoluble, and that insoluble thing I'm going to get is silver chloride. So this is the net ionic equation for the reaction that's going to happen. Okay? So the rest of these questions, we're going to skip. I would suggest you go through them. You'll see them in your homework, and you'll get an explanation for them in your homework. The best way to really be able to answer these questions easily would be to familiarize yourself with the solubility rule. So learn as much as you can about and the only way to do it is to really practice using it. So you should have a bunch of these questions on the homework that you can practice on. Okay? So like I said, a chemical equation that only shows complete formulas of the compounds is the molecular equation, right? And so this is just to recap. An ionic equation would be a better representation of the reaction when ions are involved. And so when you write your ionic equation, you write your strong electrolytes. If they're strong electrolytes, that means they're completely dissociated in water. If they happen to be in water, you write them as separate ions. And then if you remove ions that are not actually involved in the reaction, if you remove the spectator ions, you get what's called the net ionic equation. And that's the best way to represent what happens in solution. Okay? And this is the example I gave earlier. This is the full molecular equation. Okay? And then since lead nitrate is in solution, I can write that as lead plus 2 nitrates. And potassium and iodide are separated in water. So 2 potassiums plus 2 iodides. And then my product would be PbI2. Since that's not in solution, I have to write it intact as one formula, PbI2. And then my potassium nitrate right here, I'm going to write that as 2 potassiums plus 2 nitrates. Okay? So this is my ionic equation. And my net ionic equation would be one where I get rid of my spectator ions. So I remove my nitrate, I remove my potassiums, and I have my net ionic equation, which is lead ions plus 2 iodide ions gives me PbI2. Now, what would be the net ionic equation for the dissolution of sodium oxide in water? You're given the molecular equation. So what would you do here? Well, this is a solid, so you don't break that up. You just write it as is. Water is a liquid, okay? It's a molecular compound, so you write it as is. But sodium hydroxide in water, okay? It's an ionic compound in water. This is not going to give you any pairs of sodium and hydroxide in water. What you have in water are separated sodium ions and hydroxide ions. So this has to be written as 2 sodiums plus 2 hydroxides. So this is your ionic equation. Okay? So instead of writing 2 NaOH, I write 2 sodiums and 2 hydroxides. But what would be the net ionic equation? Well, you look for spectator ions, and there are none, so this is also the net ionic equation. So this is the case where the ionic equation and the net ionic equation are the same because there are no spectator ions. Right. So what happens if you have a precipitation reaction that occurs between potassium sulfate and lead nitrate? Okay. So I think you should be able to figure this one out. Let's do a poll and see what your answer for this would be. Is it A, K plus nitrate gives you KNO3 solid? Or B, lead plus 1 plus SO4 negative 1 gives you PbSO4? Or C, lead plus 2 plus SO4 negative 2 gives you PbSO4 solid? What would be the best answer here? One of these you can eliminate right away based on the solubility rules. The other one you can eliminate because it doesn't have the correct formula. Okay. Very good that you all say A is not correct. You're not going to get a precipitate that has potassium in it. All compounds containing potassium, according to your solubility rules, are soluble. Okay? So it's a choice between B and C, and it's a matter of knowing what the correct formulas are. Sulfate is SO4 with a negative 2 charge. Sulfate doesn't have a negative 1 charge. And so that means if you can see it right here from potassium sulfate, okay, you could figure out that it is negative 2 because you have 2 potassiums and a sulfate. So the sulfate must have a negative 2 charge, okay? And here, nitrate, or you should really know that sulfate is SO4 with a negative 2 charge. And you should also know that nitrate has a negative 1 charge, so that this lead right here must have a plus 2 charge. So the precipitation reaction, the net ionic equation is PbSO4, Pb plus 2 plus sulfate gives you lead sulfate solid. Correct answer is C. Okay, and this is more of the same type of question, so we're going to go ahead and skip that. Okay, let's go talk about acids now, reactions of acids. Like I said before, acids are compounds, molecular compounds that when you put them in water, they break up into ions, and one of the ions that you always get from acids would be H plus. Okay, so a common feature of the reactions of acids would involve this H plus. Okay, there may be other reactions, but if we're interested in its behavior as an acid, we're really interested in what this H plus does when you put it in water in combination with other things. Okay, so the H plus from the acids, generally, these are positive, so they tend to find negative ions to react with, so they will react with a negative ion from the other reactant. So if you have some other ions coming from some other compounds that you put in your water, then a negative ion could combine with that H plus. Or if you have a molecule that happens to have a lone pair typically on a nitrogen atom, like ammonia. Ammonia is NH3. It has a lone pair, that means an unshared pair of electrons. That tends to be attractive to a proton, an H plus. So an H plus has a tendency to just attach to it. Okay? And so that's a typical behavior of H plus in water. So the H plus that breaks off from the acid is going to go looking for something negative to join with, okay, to form a molecule or another ion, or it can attach itself to the lone pair of another molecule, like ammonia. Ammonia would be an example of what we would call a base, a proton acceptor. Remember, H plus is a proton, okay? So H plus from the acid, okay, if it happens to find a hydroxide ion or an oxide ion, what does it do? Oops, oxide is O negative 2. It can give you water. Why is that? If you have H plus, it finds a hydroxide, then it will give you HOH, which is just H2O. Hydroxide, the structure of hydroxide looks like this. It's got 3 lone pairs on the oxygen, 3 unshared pairs of electrons. So the H plus attaches itself to one of those lone pairs, and so you get water, which is going to be HOH, which you can write as H2O. Okay, so anytime your H plus finds itself anywhere near hydroxide, you can get water, or you can have 2 H pluses combined with an oxide ion. Okay, that will give you H2O. Okay, so this oxide ion might be part of a solid ionic compound. This oxide right here is not something you'll typically find in water, because this oxide ion cannot exist in water. What happens as soon as you have an oxide ion and it finds a water molecule, what it actually does is it picks up a proton from the water molecule to give you 2 hydroxide ions. Okay, so like if you have an oxide right here and a water molecule, okay, this oxide will readily pick up a hydrogen ion from water to give you a hydroxide, and leaving behind another hydroxide to get 2 hydroxides. Okay, so you don't get oxide ions in water. Any oxide that you get in water is immediately converted into a hydroxide. So that's what happens when an acid is in water. It looks for a negative ion to combine with. Okay. Now, if the acid is strong, oh, by the way, the H plus itself can attach to a water molecule. Okay, and that what you have there, once it does, then what you get is what's called hydronium ion, H3O plus. Okay, so when these two combine, you get H3O plus. So that H plus can attach itself to one of these lone pairs on the oxygen of water, and that gives you H3O plus, which is hydronium ion. Okay, so typical reactions of acids in water, okay, like I said, involve H plus combining with a negative ion to give you water if the negative ion happens to be oxide or hydroxide, or if you have another source of negative ions, the H plus plus the negative ion can give you a weak acid molecule. Now, if the acid that you get when combining the H plus with the anion is strong, then you're not going to get a reaction, because strong acids don't exist, will not persist in water. So, for example, okay, let's say I have an H plus and it finds some chloride in water. You might say, okay, H plus likes negative ions, so it will combine to form HCl. But this HCl does not exist in water. This immediately, okay, this is one of your 6 strong acids. So this is one of the 6 strong acids we learned about earlier. So this hardly happens at all. In fact, any HCl you put in water is actually going to break apart into H plus and chloride ions. Okay, so we say then that if you have an acid, you can have a reaction between it and another ion if the combination of the H plus and the negative ion will give you a weak acid. So anything besides HCl, and what are the other strong acids we have? HNO3, you cannot get that. Oops. You can't get HNO3. You cannot get H2SO4 because that's a strong acid. You cannot get perchloric acid, that's a strong acid. So these are your strong acids. You cannot get HCl, HBr, or HI. You have to remember your 6 strong acids in water. You cannot produce those molecules in water because they're just going to fall apart right away. Okay? Now, if the weak acid happens to be carbonic acid, okay, so this is what would happen, let's say, if you have to react, let's say, something with a carbonate. So let's say you have an acid, the H plus from the acid if it combines with, it finds carbonate ions in water, okay? Two of the H pluses will give you, plus the carbonate will give you H2CO3, which is carbonic acid, okay? And what happens to carbonic acid is if you build it, readily decomposes into carbon dioxide and water, okay? So it readily decomposes. So what actually happens is you don't get a whole bunch of carbonic acid because that will readily break apart into carbon dioxide and water. So the overall reaction is, so this is, you would say this part right here, that's a decomposition reaction. So the overall reaction is if you have H plus from the acid plus carbonate from, if you have carbonate in water, it's going to give you carbon dioxide gas plus water, which stays with the liquid. So that carbon dioxide is the fizz that you see. For example, when you were to mix, let's say let's say you can get your H plus from vinegar. Okay, vinegar is an acid, has an acid called acetic acid. And if you were to mix vinegar and baking soda, for example, not baking soda, washing soda. Washing soda is a water softener. It has carbonate ion, sodium carbonate. Then you get carbon dioxide. Same thing happens with baking soda because a bicarbonate ion, okay, with a bicarbonate ion, baking soda is sodium bicarbonate. So if you put it in water, it's going to give you sodium ions and bicarbonate ions. Okay, so when your H plus from the acid sees a bicarbonate ion, what will happen? Your H plus will combine with your bicarbonate ion. So the H plus, you might say, comes from, let's say if you did this at home in your kitchen, you can mix vinegar and baking soda. Okay, so your bicarbonate comes from your baking soda. Then the H plus and bicarbonate ion would give you H2CO3, which will readily break apart into carbon dioxide and water. And so you see that fizz, okay, when you mix baking soda and vinegar. And that's the reaction for that. So that's typical reactions of acid. It has to do with H plus combining with a negative ion or combining with a molecule that has a lone pair. Another commonly observed gas, this is an example of what we call a gas formation reaction. Another one is if you form H2SO3. So if you have a sulfite, SO3 negative 2, that combines with H plus to give you H2SO3. If you have a lot of that H2SO3, you might be able to generate what's called that readily breaks up into SO2 gas and water. So you're going to stink up the place. It's got a very strong smell, SO2 gas. Okay? And that can also happen if you're reacting with a bisulfite. Okay? So you ask a reaction between an acid and a sulfite would give you H2SO3, which, like I said, readily breaks up into water and SO2 gas. Or another way you can generate SO2 gas is if you react H plus with a bisulfite, H plus with hydrogen sulfide ion. So this is called bisulfite, hydrogen sulfide, and that's going to give you H2O plus SO2 gas. So those are common reactions. Those are the common reactions of acids. Okay, two major types of reactions involving acid. It has to do with the H plus. Now, the anion from the acid itself may react with something else in the solution to give you a precipitate. So, in addition to the reaction of H plus, the negative part of your acid, the anion from it, might be able to give you something else like a precipitate. Okay. All right, so what if you have a metal oxide plus metal hydroxide plus acid? Like I said, you basically get a salt and water. Okay, so your H plus from the acid combines with the oxide or the hydroxide and gives you water. So let's look at some of these examples right here. Let's look at the reaction between HCl and sodium hydroxide. Okay, HCl and sodium hydroxide. You might say, okay, this looks like, okay, something that produces ions in water, something that produces ions in water, HCl and sodium hydroxide. So if you, as we've learned earlier, okay, you can predict possible product for this would be an exchange of partners, right? H plus would combine with hydroxide to give you water, and what the remaining ions will give you your salts, sodium and chloride. Okay, acid plus a metal oxide or hydroxide gives you salt and water. Okay, that's a very basic prediction scale that you're expected to know. Acid plus base gives you salt and water. Now that would be what you would call your molecular equation. What would be the net ionic equation for this? Well, let's write the ionic equation first. This is H plus chloride. Since HCl is a strong acid, I have to write it separately. Sodium and hydroxide would also be written separately because sodium hydroxide is an ionic compound, so it's going to be completely broken up if it happens to be in solution. Water is a molecular compound. I have to write it in full, intact. And then sodium ions and chlorine ions. Sodium chloride is ionic compound, so I have to write it separately, sodium ions and chlorine ions. So what I have here, what do you call this one? This is your ionic equation. Okay, so what we have here, the first one over here, is your molecular equation. And what's the next step? If I get rid of my spectator ions, chlorides and sodiums, what's left behind? I just have H plus hydroxide gives me H2O. So this is my net ionic equation. All right, and so that would be the net ionic equation if you were to mix HCl and sodium hydroxide. The net result is if you have a strong acid plus a metal hydroxide or a base, the net ionic equation is H plus hydroxide gives you water. Okay, so this will be your net ionic equation for HCl plus sodium hydroxide. What about barium hydroxide plus H2SO4? Let's take a look at that one. You're going to say, all right, if you were to do the molecular equation, you say barium hydroxide, oops, got my subscript wrong. Barium hydroxide plus H2SO4, okay? So metal hydroxide plus acid, acid plus base gives you salt and water. So water, you can get your water from this H plus and then hydroxide, and you can see you're going to need two of those. That's two waters, and then you got two H pluses there. Plus, what remains is barium sulfate, BaSO4. Okay? So this is your, and this is already balanced, so this is your molecular equation. How do I write the net ionic equation? Well, let's see. I know my barium hydroxide is in aqueous solution because it says so right here. It's an aqueous solution. So this barium hydroxide has to be written as barium plus 2 hydroxides. Okay? It's not OH2. Don't write it that way. You have 2 hydroxides coming from barium hydroxide. And your H2SO4 is a strong acid, so I write it as 2H plus sulfate. Okay? Um, write it that way. And then my products would be H2O. Okay, so your H2O has to be written as one complete formula, right? Plus barium sulfate. Now, if you go back to your solubility rules, you'll find that barium sulfate is insoluble in water. So you would expect that to be a precipitate. So you're going to write BaSO4 solid. Okay? So that is your this is what you would call now your ionic equation. And if you examine it closely, there are no spectator ions, so this is also your net ionic equation. All right. If barium sulfate was soluble in water, if this was only soluble in water, the barium and the sulfate might have canceled out. So there's really two reactions going on here. The hydrogen, okay, to balance this, I need a 2 there. The hydrogen ion and the hydroxide ion combine to give you water. That's your acid-base neutralization, okay? There's actually two reactions going on here. Your H plus and your hydroxide gave you water, and then your barium and your sulfate gave you a precipitate of barium sulfate. So the overall reaction is a combination of both acid-base neutralization and precipitation reaction. Okay, let's look at the next one. Calcium hydroxide plus acetic acid. Okay, calcium hydroxide plus HC2H3O2. Okay, what product do we expect to get here? Okay, again, you can think of this as acid plus base. So the H from the acid and the hydroxide from the base would give you water. Acid plus base gives you water and salt. What's the salt? The salt comes from the positive ion from the base and the negative ion from the acid. So your salt would be calcium acetate. Acetate has a -1 charge. Calcium has a +2 charge. So calcium acetate would be Ca C2H3O2 parenthesis 2. Okay? So that's your, and then to balance this, I got 2 hydroxides, so I'm going to make 2 waters. 2H plus 2 hydroxides give me water. And then, okay, so that's your balance equation. This is your molecular equation. The question is, what's our ionic equation? Then you have to realize calcium hydroxide is soluble in water. I have to write it as calcium ions plus 2 hydroxide ions. Acetic acid is a weak acid. So this is a weak acid. So that's not a strong electrolyte. I should not break that up. I should write it as is, HC2H3O2, because it's a weak acid. And then water is a molecular compound. I write it intact as is. Okay, and in fact, I need to balance this, right? I need a 2 there to balance it. Okay, so I need 2 H2O plus my calcium acetate. This is an ionic compound right here. So I have to write that separately. I have to write calcium ions separately from acetate ions plus C2H3, 2 acetate ions, so 2 C2H3O2 with a -1 charge. And if you look at this, this is what you would call your ionic equation. Okay? And if you examine your ionic equation, you'll find that you have 1 spectator ion, the calcium ion. Nothing really happened to the calcium ion in this reaction. What happened was the hydroxide picked up the proton from acetic acid and then not liberated your acetate ions, so to speak. and calcium was just there, just watching everything happen. Okay, so what happened here is your two hydroxides picks up a proton from acetic acid, two acetic acids, HC2H3O2, gives you two waters plus two acetates. So this is your net ionic equation. Now this can actually be simplified. You'll notice all the coefficients are 2. There's 2, 2, 2, and 2, so you can simplify that. You can just say hydroxide ion from calcium hydroxide picks up a proton from acetic acid. So this proton is picked up by the hydroxide to give you water, and that frees up your acetate ion, H2C3, C2H3O2 negative 1. So you can reduce all your coefficients to 1. That is the net ionic equation for this reaction. Okay? That's calcium hydroxide plus acetic acid. Okay? Let's look at this last example right here. This is calcium hydroxide solid plus HCl aqueous. So here you have a reaction between calcium hydroxide solid plus HCl. Well, what products do we expect? Again, acid plus base. So H plus will combine with hydroxide to give you water. And what's the other product? Calcium and chloride together. Calcium is plus 2, chloride is negative 1, so the other product is CaCl2. And it's soluble in water, so we write aqueous. Okay? That would be your, and then to balance it, I'm going to need 2 HCl's. Okay? And I'm going to get 2 waters. So this is my molecular equation. What is my ionic equation? Well, okay, first of all, calcium hydroxide, if it was in water, it would be broken up. But in this particular case, it's a solid, so you don't break it up. You have to write it as is. Calcium hydroxide to solid. Okay? We only break up formulas when we're dealing with substances in aqueous solution that happen to be dissociated in aqueous solution, broken up in aqueous solution. HCl, that's a strong acid, so I have to break that up because it's in aqueous solution, so I have to write is 2H plus 2 chlorides. If that was HCl gas, then I have to write it intact as is because HCl gas is made up of molecules. But HCl in aqueous solution is a collection of ions, H plus and chloride ions. And then my water, as usual, I just write it as one formula, H2O. Finally, calcium chloride. Okay, calcium chloride has to be written, since it's an aqueous solution, it's an ionic compound in aqueous solution, it has to be written separately. So 2 plus calcium ions plus 2 chloride ions. So what you have here is what you would call your ionic equation. So what's your net ionic equation? The net ionic equation is what you get if you get rid of your spectator ion, which in this case is chloride. Right? So to write my net ionic equation, I'm just going to say calcium hydroxide solid plus 2H plus gives me 2H2O plus calcium ions. So this one doesn't have any of the spectator ions. This is what we would call your net ionic equation. Okay? So Those are the typical reactions of acids in water. Okay? And like I said, in addition to reacting with negative ions, an acid typically will react with molecules that have an atom with a lone pair. Typically, these molecules, the common ones you encounter, have a nitrogen in it, like ammonia. Okay, it's got a lone pair on the nitrogen that will be attracted to the proton. So you get what's called a protonated molecule. This is in fact how you form ammonium ions. So let's write the ionic equation for this. HCl, okay, is H plus chloride. Okay, it's a strong acid, so I have to write it separately. Ammonia is a molecular compound. Ammonia will react with water to give you ammonium and hydroxide ions, but it's a weak base. Okay, so the only 6 molecules that are to be written separately when in water would be the 6 strong acids. So ammonia, you write it intact. That's a molecular compound. So the only thing that's going to happen here is that that proton right there is going to attach itself to that NH3. That gives you ammonium ions. And you have your chloride ions still floating around. So this is your ionic equation. Okay? What's your net ionic equation? Well, you can see that your chloride is there before and after the reaction happened. So chloride is what you would call a spectator ion. So the only thing that happened here is your H plus attached itself to an ammonia molecule to give you ammonium ion. Okay, so acid plus ammonia gives you ammonium. Or if you're dealing with compounds, you say acid plus ammonia gives you ammonium salt. Because ammonium and chloride together, if you were to remove the water, you get a salt called ammonium chloride. Okay, but as long as the water is still there, the only reaction that really happened here was your H plus from the acid plus the NH3 molecule from the ammonia gives you ammonium ion. Okay, and again, just to remind you of the difference in the names, ammonia is NH3, ammonium ion is NH4 with a +1 charge. What if you have an acid plus a salt? Then the H plus from the acid, like I said, will react with the negative ion from the salt. If the product is a weak acid, then you have a reaction. If the product is a strong acid, then there is no reaction because you won't get the strong acid to form. Okay? So you can try some of these for practice. Okay. And you've got a few more here. Most of these remaining are just test yourself questions. And the only way to really be confident about these questions is to just try them out. I do have these in the homework, so you'll see them. And there are videos explaining the answers to these, okay? If you do want to get a head start on this without looking at the homework, you can actually get straight to the videos. If you go to camqa.blogspot.com, that's a blog that I have that have all of these typical exam questions you might encounter, which I've already incorporated into your homework, that have video explanations for the answers. So if you look at part 5, solutions and aqueous reactions, right here, write chemical equations to write net ionic equations, for example, to represent acid-base reactions. I have all of these. If you look at all of these questions I have in the presentation, in the slide presentation, they're here, and there's explanations on YouTube as to how to figure out the answers. Okay, so here's a question about the net ionic equation between the reaction between nitric acid and NH3. You have 3 choices, and here's a video that explains the answer to that question. Okay, so if you run through this video, it walks you step by step through the process of figuring out the answers. Okay, And like I said, these questions have been incorporated in your online homework, so you'll see the link to these videos from your homework if you wanted to go that route. But if you want to go straight to these videos, this is where you can find it. It's chemqa.blogspot.com. Right? So there's a whole series of questions there for different topics. All right, so let me see. Let's talk about hydrolysis of salts. Okay. Solutions can be classified as acidic, basic, or neutral depending on what we call the pH of the solution. A pH is something you can measure in the lab, okay, and it's related to the concentration of H plus by this equation right here. Basically, and you'll learn more about this in later in the course. Actually, not Chem 105, Chem 106, the next class, the next course. But the idea behind pH is that it gives you an indication of how much H plus you have in solution. Okay, so if your pH is 7, that means you have equal concentrations of H plus and hydroxide, and you have what's called a neutral solution. If your pH is less than 7, then that means your H plus concentration is higher than hydroxide, and so you have a pH of less than 7. You have a solution that's called acidic. If pH is higher than 7, then your solution is said to be basic. You have more hydroxide compared to H plus. If you recall, water, okay, can break up into H plus and hydroxide. So in pure water, you have an equal amount of H plus and hydroxide. So this happens to a very, very small extent. It's like one water molecule out of 55 billion water molecules would be broken up into H plus and hydroxide. But you can alter this balance between H plus and hydroxide by adding things to your water that will react with the water to produce H plus or hydroxide, or it could, okay? So even salts, even compounds that don't appear to have any H plus or hydroxide in the formula can lead to production of H plus and hydroxide and can change the pH of your solution, okay? So salt solutions may be acidic or basic as a result of what we call hydrolysis. And the positive ions, okay, have a tendency to, some ions have a tendency to react with water to produce H3O plus hydronium ions, which would make it acidic. Remember, H3O plus comes from H plus and water combined. Okay, and the negative ions of salts may react with water to produce hydroxide. So if only one of these two happens, then you get something that's acidic or basic. You can predict that something would be acidic or basic. But if both of these could happen, then you need a little bit more information to figure out whether it's going to be acidic or basic. So salts, we can say, can be considered acidic or basic depending on the pH of the solution that you get when you mix it with water. So cations can be proton donors, okay, and but they would be weak acids. So for example, ammonium chloride, if you were to test the pH of a solution of ammonium chloride in water, it's actually, this is a salt, right? You don't see any H plus there, but it actually will give you an acidic solution. And the reason for that is ammonium ions from the ammonium chloride will react with water, okay, to give you H3O plus NH3. It leads to a higher concentration of hydronium ions, so this is how we explain why an ammonium salt is acidic. So we say it's an acidic salt. Okay? Zinc sulfate, on the other hand, you might say, where does the hydrogen come from there? What happens is, in zinc ions, okay, zinc, when you say zinc plus 2, okay, aqueous, that's actually zinc surrounded by water molecules. Let's just put an N there with a +2 charge. That's what you would call a complex ion. The zinc ion is not really bare in water. It's surrounded by water molecules. In fact, it forms covalent bonds with water molecules. One of these water molecules, when it's attached to a zinc ion, okay, becomes something that can readily, so your zinc ions is surrounded by other water molecules there. One of these water molecules can readily produce a proton. Okay, so you get zinc, in this case, H2O, N minus 1, and one of the water molecules ends up being OH, and then that produces H plus. Okay, so one of the hydrogens can break off from these water molecules that are attached to your zinc. Okay, so these water molecules, they're tied to your zinc ion. These are called ligands. Okay, you have water molecules surrounding a transition metal. So transition metals and aluminum ions, they tend to form uh, generate acidic solutions because when they have water molecules bonded to them, the hydrogen ion from the water molecule can readily break off to give you H plus ions in solution. Okay. Conjugate bases. Conjugate base simply means that's the negative ion, the what you get when an H plus breaks off from an acid. Okay, so for example, HCl, when that H breaks off, you have H plus plus chloride, then this is called the conjugate base of HCl. Okay, if you have nitric acid or nitrous acid, for example, HNO2, when the H plus breaks off, what's left behind? Nitrite ion. So nitrite is the conjugate base of HNO2. Okay? So these conjugate bases, these ions, okay, they can combine with, they can pull a proton away from water and gives you hydroxide. That's the hydrolysis reaction, and that could lead to a pH higher than 7. So let's say, for example, you have nitrite ion, okay, or a fluoride ion right here. Fluoride ion, you can say this is the conjugate, this is fluoride that comes from HF. What happens is your fluoride ions, it will react with a water molecule, takes away a proton to give you HF, and what's left behind? Leaves behind a HF, sorry. Gives you HF, and that leaves behind a hydroxide ion. So this explains why sodium fluoride would give you a solution that has a weak pH of higher than 7, a basic solution. Okay, so anytime you have ions that can react with water to form H plus or hydroxide, that could alter the pH of your solution. And so negative ions tend to produce hydroxide when they hydrolyze. The reaction with water is called hydrolysis. Okay, and positive ions tend to react with water to give you hydronium ions. Okay, so that is all we're going to cover as far as